An instruction set of a processor is a collection that defines all the instructions. A complete instruction set is often referred to as instruction set architecture of the processor. An instruction from the set alone can be used in a program that runs on the processor. An instruction set of a processor must have the characteristics, that is completeness, efficiency, regularity, and compatibility. We should be able to construct a machine language program to evaluate any function that is computable using a reasonable amount of memory space. Frequently required functions can be performed rapidly using relatively very few instructions. The instruction set should contain expected opcodes and addressing mode. For example, if there is left shift opcode, there should be right shift opcode also. To reduce the hardware and software design cost, the instruction may be required to be compatible with those of the existing machines. So, the computer provides an extensive set of instructions to give the user the flexibility to carry out various computational tasks. The instruction set of different computers differs from each other mostly in the way the operands are determined from the address and the mode fields. So the instructions in the instruction set are classified into different types on the basis of opcode, data, operand location, operand addressing, instruction length, number of address field. No two computers have the same instruction set, but the actual operations available in the instruction set are not very different from one computer to another. Almost every computer has some unique instructions which attract the programmers. And the computer architects give considerably attention to the framing of instruction set since it involves both the programmer and the computer. Computers provide an extensive set of instruction to the user to give the flexibility to carry out the various computational tasks. The instruction set of different computer will be different. So the actual operations available in the instruction set are not very different from one computer to another. It so happens that the binary code assignments in the operation code field is different in different computers, even for the same operation. So, it may also happen that the symbolic name given to the instructions in the assembly language notation is different in different computers, even for the same instruction. Most computer instructions can be classified into three categories. One is data transfer instruction, the second one is data manipulation instruction, and third is the program control instruction. The data transfer instruction calls transfer of data from one location to another without changing the binary information content. Data manipulation instructions are those that perform arithmetic, logic, and shift operations. Program control instructions provide decision-making capabilities and change the path taken by the program when executed in the computer. The instruction set of a particular computer determines the register transfer operation and control decision that are available to the user. Data transfer instruction move the data from one place to another place of the computer without changing the data content. The most common transfer are between the memory and processor register, between processor register and input or output, and between the processor register themselves. So, now these are the 8 different um, data transfer instruction. The load instruction has been used mostly to designate a transfer from memory to a processor register, usually an accumulator. The store instruction designate a transfer from a processor register into memory. The move instruction has been used in computers with multiple CPU registers to designate a transfer from one register to another. It has also been used for data transfer between CPU register and memory or between two memory words. The exchange instruction swaps information between the two register or a register and a memory word. The input and output instructions transfer data among the processor register and input or output terminals. The push and pop instruction transfer data between processor register and a memory stack. So these are the different type of data transfer instruction. Now this data manipulation instruction. Data manipulation instruction perform the operations on data and provide the computational capabilities for the computer. The data manipulation instructions are of three types. The first one is arithmetic instruction. The second one is the logical and bit manipulation instruction. And third is the shift instruction. So, the four basic arithmetic operations are addition, subtraction, multiplication and division. So, most computers provide instructions for all the four operations. Some small computers have only addition and possibly subtraction instruction. The multiplication and division must then be generated by means of the software subroutines. The four basic arithmetic operations are sufficient for formulating solutions to scientific problems when expressed in terms of the numerical analysis methods. So one common characteristics of the increment operations when increment operation is used in processor register is that a binary number of all ones when incremented that will produce a result 0, and the decrement instruction subtract 1 from the value stores will be the decrement instruction subtracts 1 from a value stored in the register, and the number with all zeros when decremented, it will produce a number with all ones. So, the decrement operation means decrement by 1 and increment operation means increment by 1. That means in case of increment, instruction add 1 to the value stored, whereas in case of decrement, minus 1 with the value stored. So the add, multiply, subtract, divide, these are the different instructions that are available for different types of data. So these are the different arithmetical instructions. Similarly, there are some other instruction, that is add with carry. So a special carry flip-flop is used to store the carry from an operation. So the instruction add with carry perform the addition on two operands as the value of the carry from the previous computation. Similarly, the subtract with borrow instruction subtracts two words and a borrow which may have result from the previous subtract operation. The negate instruction form the 2's complement of a number, effectively increasing the sign of an integer when represented in the sign 2's complement form. So these are the different arithmetic instructions. Now, what are the logical and bit manipulation instruction? The logical instruction perform the binary operation on strings of bits stored in the register. They are useful for for manipulating individual bits or group of bits that represent the binary coded information. The logical instruction consider each bit of the operand separately and treat it as Boolean variable. So, and or XOR, these are the typical logical instructions, logical operations on individual bits of the operands. The AND instruction is used to clear a bit or a selected group of bits. So, if you do the operation x and 0, that will be equal to 0. Similarly, x and 1, that will be equal to x. That means the binary variable ANDed with 0 produces 0. But the binary variable does not change its value when ANDed with 1. Therefore, the AND instruction can be used to clear bits of an operand selectively by ANDing the operand with other operand that has zeros in the bit position that must be cleared. The AND instruction is also called a mask because it masks or inserts 0 in the selected portion of an operand. The OR instruction is used to set a bit or selected group of bits of an operand. For any Boolean variable x, the relationship x plus 1 or x or 1, that means 1. X or 0, that means x. That means it means that binary variable odd with 1 produces a 1. But the variable does not change when odd with 0. Therefore, the OR instruction can be used to selectively set bits of an operand by ORing it with another operand with ones in the bit position that must be set to 1. Similarly, the XOR instruction is used to selectively complement the bits of an operand. This is because of a Boolean relationship x XOR 1 will produce x complement and x XOR 0 will produce x. Thus, a binary variable is complemented when XORed with a 1 but does not change in value when XORed with a 0s. So, numerical example with the different numerical example we have already performed when we have done the circuit of adder subtractor. Then we have already used the properties of x and the one variable with the XOR gate. Now, a few other bit manipulation instruction is clear, set, complement, like this. So, when we will give the instruction, that means complement instruction, that means the bit can be complemented. The bit can be complemented. Similarly, clear, set and complement with carry, that are the different instruction, that is the individual bits such as carry can be cleared, set or complemented with this instruction. Another example is a flip-flop that controls the interrupt facility and is either enabled or disabled by means of the bit manipulation instruction. Next, shift instruction. Instruction to shift the content of an operand are quite useful, and these are the different shift operations, that is logical shift right, arithmetic shift right, logical shift left, arithmetic shift left, rotate right, rotate left, rotate right through carry, rotate left through carry. These are all the different shift instructions. So, shift are the operations in which the bit of a word are moved to the left or right. The bit shifted in or at the end of the word determines the type of shift used. Shift instruction may specify either logical or arithmetical shift or rotate type operation. So, the logical shift inserts 0 at the end bit position. End position is the leftmost bit or shift right, and rightmost bit position for the shift left. Arithmetic shifts use conform with the rules of the signs to complement number. The arithmetic shift right instruction must preserve the sign bit in the leftmost position. The sign bit is shifted to the right together with the rest of the number, but the sign bit itself remains unchanged. This is a shift right operation with the end bit remaining the same. The arithmetic shift left instruction instructs 0 to the end position and is identical to the logical shift left instruction. So, for this reason, many computers do not provide a distinct arithmetic left shift instruction when the logical left shift instruction is already been used. Now, the program control instruction. Instructions are always stored in successive memory locations. So, when they are processed in the CPU, the instructions are fetched from the consecutive memory locations and executed. So, each time an instruction is fetched from the memory, the program counter is incremented so that it contains the address of the next instruction in sequence. After the execution of a data transfer or data manipulation instruction, control returns to the fifth cycle with the program counter containing the address of the instruction next in sequence. On the other hand, a program control type of instructions, when executed, may change the address value in the program counter and cause the flow of control to be altered. In other words, we can say that program control instructions specify conditions for alternating the content of the program counter, while data transfer and manipulation instructions specify the conditions for data processing. Some typical type of program control instructions are branch, jump, skip, call, return. Branch and jump instruction may be conditional or unconditional. An unconditional branch instruction causes a branch to the specified address without any condition. The conditional branch instruction specifies a condition such as branch if positive, branch if 0. If the condition is met, the program counter is loaded with the branch address and the next instruction is taken from that address. If the condition is not met, the program counter is not changed and the next instruction is taken from the next location in sequence. The skip instruction does not need an address field and is therefore a zero address instruction. A conditional skip instruction will skip the next instruction if the condition is met. This is accomplished by incrementing the program counter during the execute phase in addition to its being incremented during the fetch phase. The call and return instruction are used in conjunction with subroutine. The skip branch pair of instruction causes a branch if the condition is not met, while a single conditional branch instruction causes a branch if the condition is met. The status bits, actually here we will also there is the compare instruction. The compare instruction performs a subtraction between two operands, but the result of the operation is not retained. However, certain status bit will be set as result. So these status bit will indicate the compare operation. The compare operation is being done by the subtraction method. Then the status field of interest may be carry bit, sign bit, zero bit, and or overflow condition. So the generation of these bits will be it is depends on the status. So if bit carry is set 1. That means bit C is set to 1 if the carry is 1. Similarly, sign bit is set to 1 if higher order bit is 1. That means if sign bit is 1. So bit 0 is set to 1 if the output of ALU only contains zeros. Bit overflow will be set to 1 if the exclusive OR of the last two carries is equal to 1. So these are the different status bit condition. Then the conditional branch instruction. So there are different conditional branch instruction. Each mnemonic is constructed with the letter B that denotes branch in the abbreviation. When the opposite condition state is used, the letter N for no. That means BZ means branch if 0. BNZ means branch if not 0. BNC means branch if no carry. BC means branch if carry. BP means branch if plus. BNP means branch. BM means branch if minus. BV means branch if overflow. BNV means branch if no overflow. So these are the different conditional branch instructions. The zero status field is used for state string if the result of an ALU operation is equal to 0 or not. So these are the conditional branch instruction. Branch if higher or equal. This is for unsigned number. That means A minus B. For sign bit sign comparison, also we will use the branch if greater than or equal, these type of instruction. So these are all the conditional branch instruction. So conditional branch instruction for unsigned compare condition is branch if higher or equal, branch if lower or equal, branch if equal, branch if not equal, and sign compare condition branch if greater than, branch if greater or equal, branch if less than, branch if less or equal, branch if equal, branch if not equal. So these are different conditional branch instruction. And that's all.